Welcome everyone to the fourth and final video here, talking about chemical thermodynamics. Right, talked about spontaneity, what makes a reaction spontaneous and such. Right, how it's related with entropy change in the universe and what is entropy, and then we've related that to then Gibbs free energy and what that is. Right, and how the change in Gibbs free energy of a reaction can tell us about whether or not that reaction is spontaneous. Okay. And so we're talking a little bit more about that spontaneity reaction and then how this relates to chemical equilibrium. Okay, so right, when a chemical, right, so we've talked about like entropy changes being greater than zero, less than zero, Gibbs free energy less than zero, spontaneous, greater than zero, non-spontaneous, right? Well, when delta G equals zero, or the entropy change in the universe equals zero, that process is at equilibrium. Okay, that is an equilibrium state. You're at equilibrium when that is equal to zero. Okay, so you can think of your chemical reaction, right, as sort of like a ball rolling down the hill, right? You have the ball on the top of some hill, right? Push it down, it rolls down, and it reaches the bottom, right? Now if it, there's no friction, it oscillates back and forth, blah, blah, blah. But let's pretend, right, there's friction, yada, 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 the ball settles at the bottom of the hill, right? Well, at the bottom of the hill is where you're at equilibrium chemical reaction, right? Right, instead of having this potential energy of ball rolling down the hill, right now you have a free energy change, right? Your delta G, right, gets lower and lower and lower as your reaction proceeds to form more and more products until eventually you reach your equilibrium state of your equilibrium concentrations of products and reactants, and then you stop because now you've reached the lowest possible free energy, okay? And any change in the number of reactants or products, right, takes you away from the minimum of this free energy and is no longer spontaneous because then that delta G is increasing past the equilibrium point. Okay. So again, right, if I have some chemical reaction, right, that reaction is spontaneous in forming products or forming reactants as long as the reaction is moving towards its chemical equilibrium, right? So this goes back to say the whole thing with Le Chatelier's principle, right? How any chemical reaction at equilibrium, when it's taken away from equilibrium and disturbed, it will counter that disturbance to reestablish equilibrium, right? Every chemical reaction eventually wants to reach equilibrium because that equilibrium point is the lowest free energy point for that chemical reaction, okay? So that's why every chemical reaction wants to reach equilibrium, because it's at its lowest free energy when it reaches equilibrium, and so it's always spontaneous to get to that point, right? Things always want to go to the lowest energy, right? Again, think of like a ball going down a hill, right? No matter what side of, say, a valley, right? Let's pretend you have some valley, right? No matter what side of the hill, right, of that valley you start on here, right? That ball always wants to go down that valley to the minimum, right? Whether you start on the reactant side or the product side, right? You always want to go downhill, right? And so that's the case, right, for a chemical reaction. You always want to go towards equilibrium, okay? And it's always going to be spontaneous to go to equilibrium, and then once you're at equilibrium, it's not going to be spontaneous to go away from that point, okay? So how do we relate free energy change, equilibrium, and when you're not at equilibrium, okay? So this relationship here tells us what is the free energy change not at standard conditions, okay? So delta G naught here, right, is your free energy change at standard conditions, right? And then you have plus RT times the natural log of Q, where Q, right, is your reaction quotient, okay? R, again, your ideal gas constant, T is your temperature, and then again, delta G naught is the free energy change under standard conditions, right? This is, right, delta G naught is when your pressures equal 1 bar, right, and your concentrations equal 1 molar, right? And if you remember Q, your reaction quotient, right, is say the concentrations of products over the concentrations of your reactants, right, raised to their stoichiometric coefficients, right? Well, if all concentrations under standard states are equal to 1 molar, right, then, right, and then this term goes away, right? So if I'm under standard conditions, right, Q here equals 1, natural log of 1 is equal to 0, and so this term goes away, right, and I just have delta G equals delta G naught, right? That is the standard free energy change, okay? So that's why we talk about these standard free energy changes and things like that, because we relate all of our other non-standard free energy changes to the standard value given this equation here. Okay? That the change in free energy under non-standard conditions is just equal to your standard state free energy change plus RT times the natural log of Q, where again Q is that reaction quotient, that concentration of products divided by concentration of reactants raised to their stoichiometric coefficients. Okay. And so how does this relate to equilibrium, right? Well, right, as we talked about in the first kind of slide here, right, in this video, right, when we're at equilibrium, the free energy change of your reaction equals 0, okay? So at equilibrium, okay, delta G is 0 and Q equals K, right? So this is at equilibrium, right? We just talked about, right, that the equilibrium state is when the free energy is at its minimum, and so delta G is equal to 0 for the equilibrium state. And then by definition, right, at equilibrium, the reaction quotient has to equal the equilibrium constant because you're at equilibrium, right? And so Q equals K. And so just rearrange that, right? And you get delta G equals minus RT ln of K, okay? Or you can write it, if you want to, in terms of the equilibrium constant in terms of delta G, right? Being K equals exponential minus delta G divided by RT, okay? But these are the relationships between the standard free energy change, right? Notice this is your standard free energy change, delta G naught, and the equilibrium constant K, right? Follow these relationships, okay? And so that's it for our discussion on thermodynamics, right? Where again, we talked about what makes a reaction spontaneous or not, okay? How we might measure that related with entropy, okay? Or related with Gibbs free energy, and then talk about different ways we can calculate the Gibbs free energy, and then how Gibbs free energy itself is related with chemical equilibrium, okay, in this video specifically, okay.